Welcome back to 3.1, Part 2. So here is a definition. Given that f of c, where c is some x value, so given where that the function itself is defined, meaning we're not dividing by 0 in particular, or you're not going off to infinity, if f of c is defined, then x equals c, that input value, is a critical value if the derivative is equal to 0. We also have if the derivative is undefined. That's that little corner or point cusp that we saw on the previous example at x equals 7 and x equals 9. Those are cusps. So those are where the derivative is undefined. But for the most part for our class, it's where the derivative is equal to 0. So notice that the critical values were exactly the values that divided up our sign chart. Yay! So now onward, a relative maximum or relative minimum is higher or lower than nearby points. So I've got this just arbitrary function here, and as we travel along from left to right, we've got a relative max at that first high point. And then we come down and looks like maybe somewhere in here, just eyeball it. We've got a relative minimum. And then we pop back up just for a moment, get that little tiny bump there. It's another relative max. It's certainly not a total max because there's other higher points on the graph, but it's the high point in its own little universe. So it's a relative max. Then we come down and we get another relative min. And then the graph shoots off forever up to the right, and there aren't any more relative maxes or mins. We assume that just from the shape of the graph. All the interesting stuff has happened in these 4 points in the middle. All right, so that's relative max and min. So notice that the derivative is 0 at each of the maxes and mins. So if we put a little tangent line on each of these points, the slope is indeed 0. And that's the derivative. I'm using m, but that is the same as f prime of x. However, just knowing that the derivative is 0 is not enough to guarantee a max or min. If you like, pause the recording, see if you can come up with a graph where we're going to have a moment of 0 slope, and it will not be a max and it will not be a min, neither of those. Okay, so here's an example. What if our graph comes up and then levels off as though it were going to go down again, but then decides to go back up again, all right? Right there in the middle, if I've drawn it well, there could be a moment of 0 slope, and yet it's not a max or min. Oops. Not a max or min. And we can have a similar thing happen if the graph is coming down, levels off for a moment, and then continues down again. We get a point in there where the slope is 0, the first derivative is equal to 0, but it's again not a max or a min. All right, so what does it take then to make sure we have a max or min? We're still going to look for these critical values where the derivative is equal to 0. That's still useful. But we also need to know that a graph changes from increasing to decreasing at a max, increasing then decreasing at a max, or from decreasing to increasing to get ourselves a min. So you need 2 pieces of information, the derivative 0, but also that change of slope. Okay, and that exactly is called the first derivative test because slope is first derivative stuff. So if the sign of the derivative changes as we pass a critical point, x equals c, then for sure there is a relative max or a min at x equals c. So that's the first derivative test. So as I say here at the bottom, we can fold a sign chart into a larger summary chart to describe the behavior of the function. So we'll include all that positive, negative stuff we did earlier, but we'll now also talk about max, mins type stuff as well. So again, I'm going to use the format of the book to make a summary chart. Let me scroll up here and let's work on this larger problem. So this summary chart here, if you look at the left-hand column with the what that's short for intervals and values. And so in this left column, you can see I've got the special points on the x-axis, 6, 8, and 10. These are the values, the 6, the 8, and the 10. And then in between and beyond those individual points, I've got intervals, negative infinity up to the 6. That's an interval. Then the 6. Then the interval between 6 and 8. And then the 8. And then the stuff between 8 and 10, and the 10. And then everything beyond the 10. So right away, what we can do is put in the sign of our derivative. Okay, so that's what we would have done before horizontally in our horizontal number line. So as I look at this graph, it's got negative slopes as I approach 6. So the derivative starts off negative. And then right at 6, we've got that moment of 0 slope. So I'm going to put that into the table. And then between 6 and 8, this graph is going back up. It's increasing. It's got positive slopes. And then at 8, because we've got one of those cusp situations, that point, that's where the derivative does not exist. It's not 0. We say it doesn't exist at a point. But then it starts to decrease, so we have negative derivative. We hit that 10 at the bottom, where once again we have a 0 slope. And then after 10, this graph is going up again. So we have a positive first derivative. So that, excuse me, that second column, the f prime column, is exactly what we did before with the derivative. Then what we can do is we can, for f of x, not so much for the intervals, because f of x is always changing. All these y values are different as we move along between those critical values. Those y values are all different, so we're not going to put anything into our f of x column for the interval parts. But at x equals 6, we actually have a y value given to us. That point right there is the point 6, 4. So we can say that f of x is equal to 4 at the point 6. The slope is 0, and the y value is 4. So that f of x column is asking for a y value. So we've got 4 for 6, and again at x equals 10, that point is 10, 4. So the y value for x equals 10 is 4. And then the y value at x equals 8 is 9. So we've got a point at 8, 9. So the f of x column, we can be very specific. And then as far as the behavior of f, we're going to go back to some of the vocabulary that we had at the beginning. So when we have a negative first derivative, when the graph is going down, the word that we use is decreasing, or just d, see? Then the graph hits that point at 6, 4, and you can see that it's a low point. And our word for that is minimum, or min. We've got a minimum at that point 6, 4. Then the graph starts to increase. Positive first derivative means it's increasing. Then we hit a maximum at 8, 9. And then we're decreasing again as we approach x equals 10. We hit another min at x equals 10, and then the graph starts to increase again. So it seems obvious. The picture is right there in front of us, right? So part of what we're doing is practicing using some words like increasing, decreasing, and max and min to describe what's going on in the graph. And we're also reinforcing, reconnecting the idea of slope as telling us whether the graph is increasing or decreasing. And then y values are giving us locations. So what I might even do is really emphasize that we have a minimum at the point 6, 4. We've got a maximum at the point 8, 9. and we've got another min at the point 10 comma 4. All right, so just expanding our ability to talk about graphs. And I'll encourage you, instead of, I often say the graphs go up and down, but try to use the words increasing and decreasing. Okay, so I think I will end this part of the video also, and then we'll come back and we're going to do stuff without graphs. We're going to start looking at actual functions to do some of this same work. So see you in part 3.